Okay, let's get started. And today is our sixth lecture, finite volume method for the Euler equations. First of all, I'd like to finish the previous topic, and so the current topic, the topic of current lecture will be the continuation of the previous one. The previous lecture was dedicated to the analysis and to the construction of the numerical methods for the linear advection equation. And actually, we constructed and discussed the main properties of three, well-known and apparently, from historical point of view, they were among the first, good, workable methods for the linear advection equation. So the first one was the Courant Isaacson Rees numerical scheme, or theorem scheme, and it also called the scheme on the stencil left angle, because if lambda is greater than 0, then the stencil for this scheme is comprises 3 points, 1, 2, 3, like an angle to the left. And we proved actually that this scheme, we carried out the consistency analysis, and we proved that the accuracy order for the scheme is first both in time and space, big O of tau and h. And we also introduced and discussed the concept of monotonicity, and the Courant Isaacson Rees numerical scheme is monotone. That's because for the range of sigma, and sigma is Courant number, lambda tau over h, for sigma greater than 0 but less than 1, all the coefficients of this scheme, alpha minus 1, 0, and alpha 0, 0, they are both greater than 0 or non-negative. And that is why the scheme is monotone. And here I provide the sample of simulation result for the advection of a square wave. So the red line is an exact solution, and the blue points and blue line is the numerical solution. And I took lambda equals 1, sigma equals 0.5, and h 1 to minus 2, and computed 150 time steps. And for all numerical schemes, I carried out the same manipulations, and we can compare simulation results obtained using different numerical schemes. So we discussed that there are pros and cons of these results. For example, the disadvantages of usage of low order scheme, of the first order scheme, include the smearing of shocks, smearing of discontinuities. So instead of very sharp changing of our function, we have very smooth changing of our parameters, and actually that's not good. So another disadvantage is that the amplitude of the signal decreases in time, and that's also not so good. But at the same time, from physical point of view, this solution is physically relevant. Actually, it means that, what does it mean that the scheme is monotone? It means that at the range where the solution should increase, the numerical solution increases, and in the region where the solution should decrease, the numerical solution decreases. And in this sense, you can take h 1 to minus 3 or minus 4 or minus 5, and if your computational facilities are, you have enough, your computational facilities allow you to do such simulations, you can take smaller cell size and obtain more accurate result, and it will be physically relevant. So actually, that's why first order schemes are maybe not so bad. It depends on your problem. If your time scales are not so big, maybe and the question is to understand the physics of the process, maybe even the first order scheme is not so bad. So this is Courant Isaacson Rees numerical scheme. The second one was the Wendroff scheme. So we decided to but generally speaking, first order, the big O of tau and h is not enough, and it would be great to have the second order scheme. And we proposed the Wendroff scheme. So the Wendroff scheme was constructed as the correction to unstable scheme with central difference. So this is the scheme with central difference. Explicit approximation in time and central difference for du over dx derivative in space. And it is known that this scheme itself is unstable, and we corrected it. We subtracted the approximation of the leading term of truncation error. And on this way, we obtained the Lax-Wendroff scheme. And we discussed that each of the scheme can be rewritten in the following form, in the form of linear combination of these products, root function and some coefficient, unknown coefficient, if we would like to build the whole family of numerical schemes of a certain accuracy order. But so these coefficients do not depend on u, so they depend only on Courant number. And this is the stencil for Lax-Wendroff scheme. So the stencil now includes m+1 endpoint. So it's the biggest stencil, 4-point stencil. And this is the example of simulation result. And so this is again a very typical picture for the second order schemes, because of tau h and of tau squared h squared. And here we also discussed that the main disadvantage of this scheme is that we have spurious oscillations, unphysical oscillations. This effect is called overshooting when your numerical result is higher than the exact solution, and this is undershooting. And at the same time, the localization of this discontinuity is much better in comparison with first order scheme, because you can see it's non-zero values here and here only just near the discontinuity. And but nevertheless, this scheme is not suitable for practical simulations, the problems with shock waves, because you are not able to make a distinction between unphysical oscillations and physical oscillations. If your problem includes some a number of shock waves and refractions, reflections, and you need to understand what's going on. And for example, if you analyze the pressure sensor, the pressure record from some point, and you see some oscillations, you're not able to make a distinction between physical effects and the numerical effects. That is why this scheme is also not so good, but the reasons are different, right? So pros and cons for different schemes, for all schemes. And from a mathematical point of view, it means that the Lax-Wendroff scheme is non-monotone. Non-monotone. It means that on the part where solution should decrease, it produces the numerical solution with changing character of monotonicity. It means that we get this region of decreasing of our function, and that's not true. The result is not valid in this sense. And the last one was the Lax scheme, or usually is also called Lax-Friedrichs scheme in literature. And this scheme is monotone actually. So all the schemes, so the Lax-Friedrichs scheme and Courant-Rees scheme, they are monotone and stable if Courant number between 0 and 1. And we demonstrated it for Courant-Rees numerical scheme from geometrical consideration using characteristic analysis and CFL condition. Actually, it's possible to do using so-called spectral criterion or von Neumann criterion, but we did not do that. Maybe later we will do it. Anyway, so the typical restriction for explicit scheme, and all these schemes are explicit. So what does it mean explicit? Because you have this explicit order scheme for time integration, and so all parameters here are taken from nth time layer, n, right? It means that we can do one step, and we know everything to do that. We did not discuss, and we are not going actually to discuss implicit schemes, where, for example, here you have n+1, and it means that on each time level you will have the, generally speaking, nonlinear problem, nonlinear algebraic equation if you solve nonlinear equation. And actually there are also very interesting topics in this regard, but we're not going to consider it now. So we considered Lax-Friedrichs scheme, And how can it be obtained? We can again take the unstable scheme with central difference and then substitute this umn using this 1/2 of minus 1 and plus 1n. And then you will get the scheme that's you can use it in practical simulations. So now we excluded this point from the stencil, so it's a 3-point stencil, and again it can be written in this form, and this is the simulation result. And actually, you can compare this first order scheme and this first order scheme, and you can see that this first order scheme is better than this one, actually, because at the same time instant the amplitude of this of this signal is higher than this one, and also you can see here the non-monotonicity of first derivative of function. And when the profiles from this part and this part meets, then the profile becomes itself non-monotonic, although the scheme is monotone itself. So actually, generally speaking, this first order scheme is worse than this one, and actually this one is the best first order scheme. And so we discussed all these properties and how can we build these schemes, and then we generalized the scheme using these unknown coefficients alpha. So we mentioned that actually it turned out that all these schemes can be written in the same form, and actually in this form. So n plus 1 equals this superposition of grid function with coefficients alpha. And we analyzed these equations for consistency. So the question is it possible to construct all possible numerical schemes of different accuracy using this general notation? And we carried out consistency analysis. We used Taylor series expansion for these and these guys, and then put them into this formula, and then obtain the system of linear equations for alpha. And so this is the general stencil, right? So this general stencil covers this one, and many other numerical schemes. So all the numerical schemes that we discussed, they're here, okay? And the only question is how can we, classify it and compare all these schemes between one another or each other. And we obtained a system of equations for alpha, and said that if you take only two conditions, then the family of first order scheme is a two parameter set. It means that, for example, if we take alpha minus 2, 0, alpha 0, 0 as 3 parameters, and plot this space, then each point on this surface will determine the first order scheme, some first order scheme. And then we introduced the definition of monotonicity. So monotone schemes. So a scheme is said to be monotone if all the coefficients are non-negative. If you're talking about this linear scheme for linear direction equation. And for linear schemes, so this definition is equivalent to monotonicity preserving property. So monotonicity preserving property is obvious from practical point of view definition. So we want to have monotonicity preserving schemes because they do not produce spurious oscillations. So if you have monotonic part of our solution, at some time instant we want to have the same character of monotonicity at the next time step. And for the linear direction equation, it's the same, that all the coefficients should be non-negative. That is why on this space we would like to find the schemes for alpha, for non-negative alpha. And we also plotted this area of monotonicity A1, A2, A3, and 4, and we pointed out the schemes that we just discussed. So this scheme A2 is Courant-Jackson Rees numerical scheme, and this point is like Friedrichs scheme. So the green line is set of second order schemes, and for this stencil, it's possible to build only one numerical scheme with the third order of accuracy. And these coefficients define this numerical scheme. And so A1 is Lax-Friedrichs scheme. And so actually this consideration was carried out by, I graduated from Moscow Institute of Physics and Technology, from Department of, it was called Calculus Mathematics. Now it's Department of Computational Physics. And the former director of this department, Professor Kholodov, he, carried out this analysis. And you can see that, so I mentioned that there is so-called Godunov theorem. There are no linear monotone schemes with the order of accuracy greater than 1. So it is, famous paper. We also discussed it. Godunov proved that this green line corresponding to the second order schemes, it cannot intersect with this quadrilateral corresponding to monotone schemes. But at the same time, you see that this A2 point is much closer to the space of second order schemes in comparison, for example, A1 and A4. And surprisingly, if you compute some test using A2 scheme or A1 scheme, you will see that actually A2 scheme is more accurate. So the hypothesis when people constructed this space was maybe the schemes that are close to each other in just our ordinary Euclidean norm, maybe their properties will be also close when we will do some simulations. And to some extent, this hypothesis was proved. And actually, indeed, these properties of A2 scheme, Courant Rees scheme, they are better in comparison with the Lax scheme. I didn't show you simulation results for this C point, so now you can see it. So this is the simulation result for the only possible third order accurate scheme for this stencil. And you can see it's also non-monotone. We have spurious oscillations, but in contrast to Lax-Wendroff, they are almost symmetrical, although not exactly. But the scheme oscillates on both sides of our square wave. But actually, you can see that the result is much better than Lax-Wendroff scheme, right? Because a lot of oscillations and they go left, and here the oscillations are localized. They're just small overshooting and undershooting. So that's also not bad result. Okay, so we analyzed all these schemes, introduced definition of monotonicity, and so monotone preserving schemes, and established some relationships between these schemes. Yes, I can share the code. Actually, we had a lecture dedicated to practical implementation of numerical scheme for linear ordinary differential equation. Actually, the code is just almost the same, but here the main difference is that now we have a time cycle, because we have now two variables, time and x. So we have time cycle, and inside time cycle we have cycle of our computational cells. And so the whole parameter, the whole problem is defined by initial profile. Actually, the square wave or step is the most difficult initial condition, because all these spurious oscillations usually occur only on discontinuities. But if you take, for example, smooth solution like this one, you will see that the Lax-Wendroff scheme also works well. And so if you have very smooth solution, even high order methods work well. So you should define the number of nodes, the number of time steps, define a problem. Lambda is the advection velocity, define your boundaries. So if for example, we would like to compute our, to solve our problem in the segment from 0 to 2, and define the boundaries of our square wave, and define the Courant number. So usually in these problems we fix the Courant number, and if we fix the Courant number, it means that we know the time step. So dt is sigma h over lambda, and so we start with the initialization of our numerical solution. So we get exact solution at 0, t equals 0 is the initial profile, and then start our simulations. And so I implemented Courant-Jackson-Rees scheme, Lux-Wendroff scheme, Lux-Friedrichs scheme, and third is the only third order scheme. So actually, again, these expressions can be obtained analytically when you solve 4 equations for 4 unknowns, when you carry out consistency analysis for this general formula. So you get these coefficients as functions of sigma, and then you choose some value of sigma. Actually, you can take sigma between, for example, 0 and 0.5. For example, 0.25. You can also, so this result depends on sigma. So if you will choose another value of sigma, it will change somehow. So you should know that all this, so it's just, some typical results. So if you change the time instant, will take not 150 time steps, but longer. If you change current number, so you will get different results. But the tendencies will be the same. And so this is the example, how can we implement. So I just implemented this formula. So it looks like a bit, scary, but it's very simple. And that's it. And you do such simulations, and they also compute the exact solution at the initial time, at the final time instant, and that's it. So the program is very simple. So I pay attention to that because one of the lectures will be dedicated to. So when we'll reach the topics on gas dynamics, so you will see that the structure of typical program for gas dynamics simulations for the solution of Euler equations for gas dynamics. So in many things it's just the same like this one. So that is why I started with very simple programs, and then so the next step will be more difficult. Okay. So one of possible way how can we generalize all our numerical schemes is the usage of the space of undetermined coefficients alpha. But this is more for theory. So, but more practical approach is moving towards finite volume schemes. So the approach that we use is called finite difference formulation. So what does it mean, finite difference? It means that we have x-axis and we have nodes m, m-1, m+1, and we know grid functions at our nodes. And the idea was, okay, let's take our initial differential problem and let's substitute somehow the derivatives. So du over dt was substituted by this explicit order scheme. So this du over dx was substituted by this, backward order scheme again. And we told that, so actually we're interested in both sides of lambda because in nonlinear case, we do not have some prescribed value of velocity of propagation of our disturbances. And we discussed that for lambda is greater than 0, this scheme is stable on the left angle stencil, and for lambda less than 0, this scheme is stable. And we also provided another interpretation of the scheme using current number. So this is an approach called finite difference formulation. Instead, we can provide the approach called finite volume formulation. Actually, now we'll show you, right? It's also actually the reminder of previous lecture. It's not the finite volume formulation because for the finite volume we should integrate. We should use the integral form of our equations. And later for Euler equations I will show you. But it's a sort of finite volume formulation. Anyway, it's just the first approximation. So the idea is that anyway we should move from our quasi-linear form here, just linear form, but in non-linear case it's quasi-linear form. So we just move this lambda to parentheses and substitute. So say that lambda u equals f. So now this is one quasi-linear form, and this is the conservation form. d over dt plus df over dx equals 0. And the idea is that we need to approximate this equation, not this one. And on this way, we can produce this, proposed general formula. So, okay, let's, again, within the scope of our course, generally we will use just first order scheme for approximation in time. only at the end of the course we will discuss that actually we can take more accurate approximation of time derivative. But actually, for all the theoretical considerations, usually we will have this explicit Euler scheme. But now this convective part. So for Euler equations, this df over dx is called the convective part. So now it can be approximated not just some derivatives to using backward or forward. We use the numerical approximation for this f. So f is numerical flux. So f is just flux, and f m plus 1/2 n is numerical flux. And so this formula is called the finite volume method. And the idea is that almost all the numerical methods that are used in practice, such as Courant, Isaacson, Rees, Lux, Friedrichs, or Lux, Wendroff, they can be formulated in both in finite difference view and finite volume formulation. And the only difference in finite volume formulation, you will have the same formula. The only difference is how to compute this numerical flux. And you can check that. This notation and this, they are just equivalent for linear advection equation. But very important, so for nonlinear, you'll get different results. But here, you will get so you have another interpretation. Now we have also nodes, m minus 1, m plus 1, but also we have cells. So we introduce cells, as volumes. And the parameters with fractional parameters, m plus or minus 1/2, they correspond to edges or boundaries between computational cells. The computational cells are also called control volumes or finite volumes. So actually, strictly speaking, finite volumes can be not just computational cells. You can build schemes on some other principles. But anyway, usually the computational cell is the same as finite volume or control volume. And you formulate your numerical scheme as a balance approximation of physical balance law. So the changing of the quantity in the control volume in the computational cell is due to fluxes of your value. And this is a very physically relevant approach. That is why the finite volume formulation actually is the most commonly used nowadays in almost all software and in-house solvers everywhere. And today we are going to discuss this approach, and we want to formulate it for Euler equations. So from today, jokes aside, we move on to more serious things, to Euler equations, not just for toy models or simplify models. And the question is, okay, when we used finite differences and when we use this general notation, we tried to build, in some sense, the best numerical scheme. So, for example, this C scheme, the third order scheme, in some sense is the best one, or at least it's some unique numerical scheme, because it's not possible to build more accurate scheme for this tensor. Yes, so the scheme is not monotonic, non-monotone, but anyway, so there is some classification and gradation between these numerical schemes. Is it possible to do some similar manipulations and to find? So I told that so all numerical schemes can be almost all numerical schemes can be written in this form, and the only difference is how to compute the numerical flux. Is it possible to find the best numerical scheme that can be built on this way? And the answer is actually yes. And there is some the best numerical scheme, the best finite volume numerical scheme, and not the best, but some distinctive scheme that is higher than any other scheme. It is called Godunov scheme, and it is based on the exact solution of the Riemann problem. What does it mean? So now just forget about the numerical solution. So again, let's just analyze our differential problem. So consider our linear advection equation d over dt plus lambda d over dx equals 0 for lambda, for example, greater than 0. And let's solve this Cauchy problem or initial value problem with the discontinuity in the initial solution. So let's choose this initial function in the form u1 if x is less than 0 and u2 if x is greater than 0, where u1 and u2 are just constants. For example, greater than 0, so u1 and u2, and here x equals 0. And the question is what the solution will look like for arbitrary time instant t. The good news is that we know the exact solution of this problem. We discussed it. So the exact solution is u0 of x minus lambda t. So the exact solution of the linear advection equation is the advection of the initial profile in the direction of in the positive direction of x. So it means that let's compute the exact solution at x equals 0. For that, we should just put this 0 to exact solution. So u exact of 0 in t is u0 of minus lambda t. But u0 of minus lambda t, lambda is greater than 0, t is greater than 0. This guy is negative. u0 of something negative is u1, because u1 if x less than 0. It's obviously, so we need to know the exact solution here. The exact solution in time is the propagation of this profile. Just from the initial time instance, this step will propagate to right, and it means that at x equals 0, we will get u1 at any time instant. So just because of the structure of our equation, so it's not about numerals, right? It's just a property of our linear advection equation. Just because of our linear advection equation, because of lambda greater than 0, the exact solution of this problem is at x equals 0 is u1. And then the idea is as follows. So when we compute the numerical flux, so let's assume that numerical flux depends only on parameters to the left and to the right. I mean, the idea is that to compute the numerical flux, let's assume that it depends only on umn and um plus 1. So actually it follows from, we also discussed it today, that all these equations that we would like to solve, we would like to know how to solve, they're hyperbolic. And hyperbolic equations are characterized by some finite velocities of disturbances propagation. So it means that if we take small enough time step, it means that disturbances do not have time to propagate from these cells or these cells to here. That is why if our time step is small enough, the numerical flux depends only on parameters here and here. And that is why we are interested in the solution of Riemann problem, because locally we have this Riemann problem. So let's just forget at the second about our numerical solution and say that if we would know from theory how to compute, so what the parameters will be here for the initial value problem for the parameters to the left, umn and umn plus 1 to the right, then we can use the exact solution of this problem to compute this numerical flux. So the idea is to couple the numerical scheme with the properties of our the solutions of our equation. So so initially it was formulated for Riemann for barotropic Euler equations. So I will give you some historical note later when we will discuss this problem for gas dynamics. So once again, this is the simplest possible Riemann problem, just for one scalar for linear advection equation. Actually, we also discussed the Riemann problem for scalar conservation law, for the Burger's equation or Hopf equation. And in a couple of lectures, we will discuss the Riemann problem for the Euler equations. So this is very important, the keystone of finite volume methods. We should know how to solve Euler equation, Riemann problem. So okay, just for linear advection equation, we know how to solve the Riemann problem. So it will always u1. And then Godunov, Sergei Konstantinovich Godunov, academician of Russian Academy of Sciences. Actually, I was at a number of his lectures. Surprisingly, he's pure mathematician. So at the beginning of his career, he was engaged in the development of these numerical methods because at that time, as I also told to you, there were no distinctions between applied mathematics, computational mathematics, pure mathematics. They were just mathematicians. That's it. But actually, he is pure mathematician, and he developed his numerical scheme. And after that, he solved more analytical problems. He suggested the following, and again, he did not suggest in there is a number of funny stories about how he developed it. Actually, this was just in chance. He realized that he, developed a new scheme after he implemented the numerical scheme in code. And at that time, it was very important how can you write a code, because the computers were didn't have enough memory, enough speed, and you should, write your code very carefully. And just from practical point of view, some quantities were combined in some combinations. And he realized that these quantities, they look like some combinations from gas dynamics. And then he understood that his scheme can be interpreted as the solution of Riemann problem. So what's the idea? The idea is that we need to compute our numerical flux, and numerical flux depends on the parameters to the left and to the right. And the idea is as follows. Let's compute the exact solution of our Riemann problem for these two states, and then put this exact solution to flux. I mean to this flux. So this is just flux or differential flux. Here for linear direction equation is lambda u. We don't know u. We don't know u here at the boundary. We know u here and here, but we need to compute flux. And the idea is, let's compute the solution of the Riemann problem. Take this u get this solution at the boundary, and then put it into differential flux. That was ultimately the idea of Godunov, and how is it implemented for linear direction equation. So we should take exact solution as function of umn and um plus 1 and put it in the differential flux. But the exact solution of this problem is the left state. We obtained this result. For linear direction equation, for lambda greater than 0, the exact solution at some point is the left state, just because lambda is greater than 0. And so characteristic line, so the inclination, like this one, that is why we always should take the left state. But the left state is umn. And once again, just because of the structure of our equation, just because we know what equation do we solve, not just press the button and so expect that the numerical method from ANSYS or OpenFOAM, just like Hammer, provide you the solution. So we know the structure of our solution, and on this way we obtain the numerical flux lambda umn. And surprisingly, if we compute in the same manner fm minus 1/2, we will get again Courant-Jackson Rees numerical scheme. So this is fm plus 1/2. This is fm minus 1/2. We can move lambda outside parentheses, and once again we will get the Courant-Jackson Rees numerical scheme. Just because this is a linear advection equation. For linear advection equation, almost all the concepts from numerical schemes they are equivalent. That's not the case for nonlinear schemes. But here the most important is the idea that here we did not, decided just to, take one or another approximation of our derivative with respect to x. No, we, obtained this scheme as a result of approximation of our balanced law. Actually, not exactly. So we should work with integral relationships. I will show you for Euler equations. But anyway, it's not the same as finding differences. And it was done. It was done in this paper. I already mentioned it at the previous lecture. Actually, in this paper, there were a lot of many important. He contributed with the same items. So first of all, Godunov theorem. There are no linear monotone schemes with the order of accuracy greater than 1. So it's not possible to build, the scheme like Wendroff without these process relations. It's forbidden. How can we solve this issue? So we move towards the nonlinear schemes and nonlinear stability. So we should provide, so actually, roughly speaking, the best schemes for the solution of order equations, they are nonlinear, and they change their properties depending on the current local properties of the solution. So the scheme should analyze the properties, local properties of our solution, and try to compute the next time steps without these previous oscillations. We are not able to use the same set of coefficients and expect that in all situations we'll get monotone profiles. We should use one or another, switching between different schemes and so on. So that's the idea, how to solve, how to overcome this restriction. So first of all, he defines monotonicity. So it was that paper where these definitions were. You can find them actually not only in this paper, but you can find them. And you can find the proof that two definitions of monotone schemes they're equivalent, and also theorem about the relationship, different scheme based on the solution, finite volume approach. The idea that we can use the solution of Riemann problem. So everything is here. So in fact, this curve for Courant-Jackson Rees numerical scheme, it can be said that it's also the Godunov scheme, because for linear advection equation, the finite volume scheme, so the Godunov scheme and Courant-Jackson Rees scheme are the equivalent. They're just the same. We have 5 more minutes, right? Okay. And some historical background. So all these schemes approach were developed in 1950s. So everything started with this paper of von Neumann and Richtmeier, a method for the numerical calculation of hydrodynamic shocks. Before that paper, that was not obvious and established in the community that it's possible to compute all the problems without consideration of each shock separately. So actually, they developed, so they explained, so they justified the shock capturing methods. So there's a term shock capturing method. So all these methods we discussed, they are shock capturing. It means that you can compute the flow field in your computational domain without consideration or take into account which type of solution do you have. So we can have shocks or rarefactions or contact discontinuity or whatever. So we can compute it using the same numerical method. That was not that was questionable. And the problem was that people do not know how to compute shock waves because a number of methods didn't work with the shocks, and they introduced the concept of artificial viscosity. So they suggested to add some viscosity in your numerical approximation to make your numerical scheme more stable. It was done in this paper. And at that time, there was a competition between the United States and Soviet Union, a number of big projects, and actually Godunov, he published actually a book and also paper, memories of different schemes, and he with information, how did they do that? So in the autumn of 1953, Kholodov is the academician, so the director of scientific research on Soviet space and atomic projects. And Gelfand is one of the most famous mathematicians of this time. So they headed the research of these projects. And so they suggested that I develop a variant of the method published by Neumann and Richtmeier. So actually they knew this paper and they realized that so it works, and they told to young Godunov, the academician of future, that we also should have such scheme. We also should do such simulations. And consistent in the introduction of artificial viscosity in the equations of gas dynamics. So to compute these shock waves at that time, they introduced the artificial viscosity. Now each numerical scheme, like Courant-Jackson Rees or Wendroff, they include artificial viscosity itself. So because of these additional terms, leading terms of truncation error. Actually, it can be estimated, this viscosity. And insistent reach was expressed to complete the development of an algorithm suitable for serial calculations of engineering problems by the spring of 1954. So you can see very, tough deadlines. So they started in autumn 1953, and by spring they should have a program that can be used in real computations. They did not have enough time. When the first instance of the Strela, so it's one of the first Soviet computers, electronic computer, was to appear in our institute, an instance from which serial production was to begin. And at that time, the paper of flux, it was not published. Maybe it was published a bit later. And with this Lux Friedrichs scheme, the third one. So this scheme was published in 1954. This one. And actually, the Godunov scheme is this one. If we reduce all nonlinear schemes to the linear case, and Godunov told that if he would know this paper, maybe he wouldn't develop his own scheme. In the United States, the finite volume method was described in, so it's a number of books and papers with this history, and the common point that the finite volume method was described in an unpublished report of the Los Alamos National Laboratory by Lux in 1953. And after that, it was actively used in all national labs like Livermore's and Deer National Lab in the USA and so on. And later, it was published. And actually, so this is the famous publication by Lux, weak solutions of nonlinear hyperbolic equations and their numerical computation. And so only in 1959, so the paper of Godunov was published, and for many years they did not know about each other. So although actually, for sure, they tried to follow the papers of each other. So it was very interesting, period in time. Okay, let's have a break. Oh no, we have for 5 more minutes, right? 50. Yeah, okay. And so everything was for just linear advection equation. Now the second part of the lecture will be about the Euler equations. So now we should use all this knowledge and from linear advection equation and apply it to our Euler equation. So first of all, let's remind what we know on Euler equations. So the first lecture and the second lecture we discussed the component-wise notation of conservation form of the Euler equation. So conservation form of the Euler equations, it means differential form first, and second, differential form written in the form of conservation laws. Mass conservation law, momentum conservation law, energy conservation law, and also entropy inequality, which is also not written but implied. So the component-wise notation means that we write each equation separately, and also it should be closed by some equation of state. So we have an expression for E, it's the total energy per unit of mass, with the kinetic term and internal energy term, and we should choose somehow the expression for internal energy, for example, ideal gas equation of state. And for numerical solution, the vector notation is more attractive. We introduce vector of conservative variables and flux vector. And then our Euler equations, so equations that we would like to solve, looks as follows: d over dt plus df of u over dx equals 0. And so we use this bold straight notation and letters for vector quantities. So this is for u, this is for f. As I told, the finite volume, the real finite volume method should be based on integral form of equations, because we want to solve the issue: how can we compute the shock waves or discontinuities, the solutions with discontinuities. That is why we should build our numerical scheme based on integral laws. That is why the integral form of the Euler equations, actually we also discussed it on the first lecture, but we didn't provide this general notation. We considered the control volume in the space xt from AB to T, or maybe this T1 and T2. That's an error, misprint. And so consider arbitrarily control volume in this space. So AB and T1 and T2 just arbitrarily coordinates and time instance. And we know that inside this control volume there are values defined by conservative variables vector, and there are fluxes through the boundaries. So flux is defined by this flux. And all mass, momentum, and energy conservation laws can be written as follows. So the integral from A to B of the difference of these quantities in this control volume, they are due to fluxes through the boundaries B and A. And so we will take this integral form of Euler equations and apply them to one computational cell. And on this way, we will obtain the finite volume method. Now we would like to build finite volume methods for the Euler equations. For that, we should use the integral form of equations. So once again, this is the integral form of Euler equations written for arbitrarily controlled volume from A to B in x and from T1 to T2 in time. And the idea is to apply this integral form to one computational cell. So here A and B just arbitrarily coordinates on x-axis. Let's take it x minus 1/2, x plus 1/2 corresponding to the boundaries of our computational cell. And these T1 and T2 just arbitrarily time instance. Let's take T1 and T2 as Tn plus 1, I mean current time layer and next time layer. And so let's do that. We substitute A and B with xm minus 1/2, xm plus 1/2, and T1, T2 as Tn plus 1. So there's some misprints and should be. So usually the subscripts are used for spatial indexes here in these lectures, and superscripts for time indexes. And yeah, here T2, T1 we take into account. And after that, we introduce the following quantities, UMN. So UMN is cell average of our function U. So here in these equations, U and F are not the grid functions. So there's some real functions. And then to get grid function, so this is a sort of discretization, approximation. That is why we should average our function. And this is the cell average of our function, UMN. And in the same manner, we should propose some approximation to the average flux along x equals xm plus 1/2 for this guy. But actually, we do not know the exact value for this integral because of this u. We do not know our solution here. We should propose some approximation. And on this way, we obtain this formula, actually, that looks just the same as for just linear advection equation, but strictly speaking, it should be obtained by averaging in time and over the volume of our computational cell. Although the final result is almost the same, you should keep in mind that here U is not just the grid function in the center of your computational cell. So strictly speaking, U is cell average function, and F is approximation to this guy. And this can be important, for example, if we try to build high-order numerical scheme such as Wiener scheme and so on, and we produce and we have some assumptions on the distribution of this function U here, and then it may be important. But for sure, from practical point of view, you can forget about this and think that you have this some averaged quantities in cell centers of your cells and some fluxes through the boundaries, even though they are obtained from this integral form of Euler equations. And as I told, so now the question is how to compute this numerical flux. And the idea is that numerical flux, at least for the schemes of the first accuracy order, should depend on values to the to the left and to the right. So for hyperbolic problem, information propagates with finite speed. We will discuss it. So it's reasonable to first suppose that we can obtain this numerical flux based only on the values umn and plus 1n. The cell averages on either side of the interface. So this is from Levesque's book. Then we might use a formula of the form. So actually, this numerical flux is some function f of these two arguments. So usually in papers, people do not introduce this, f and say that this f is a function of umn and plus 1n. And then the finite volume method becomes. So numerical flux is a function of two arguments. Numerical flux through the right boundary, or h of our computational cell, and numerical flux through the left boundary of computational cell. The specific method obtained depends on how we choose the formula f, this beautiful f. But in general, any method of this type is an explicit method with a 3-point stencil, meaning that the value n plus 1 will depend on three values. So this one, and this one. So in fact, we have 3-point stencil at the previous time layer. So again, we consider only explicit schemes. Moreover, it is said that to be in conservation form, since it mimics the property of the exact solution. I mean, what the property? The property that we started with the integral form of Euler equations. Now we can sum this h times n plus 1 over any set of cells. So we compute this sum, and the fluxes I also explained it at previous lecture. The flux through the right boundary of the cell I will cancel out with the flux through the left boundary of the cell I plus 1. They just cancel out, and ultimately you will get that the some quantity, the total amount of mass or momentum or energy in some number of cells, it's just the same as it was previously, minus, and so only fluxes through the boundaries of extreme edges. So the sum of the flux differences cancels out, except for the fluxes at the extreme edges. Over the full domain, we have exact conservation except for fluxes at the boundaries. So that's one of the most important properties of finite volume methods. Why do we like it? Why do we use it? Because they have this conservation property. Because on this way, so if we use a finite volume scheme, maybe you can make some errors here. So for example, you have errors in your numerical flux, and your solution may be not accurate. But anyway, you will get the conservation of all physically relevant properties, and that's very important. And as for linear advection equation, the most question is how to approximate this numerical flux. And actually, the following lectures will be about the Godunov scheme as the scheme for the computation of numerical flux based on the exact solution of Riemann problem, as well as a number of approximate Riemann solvers such as HLL, HLC, and today we will discuss actually approximate Riemann solver based on characteristic properties of the Euler equations. So today I'd like to show you how can we generalize the Courant on Rees for linear advection equation to Euler equation and to get this numerical flux. So today actually we are going to discuss one scheme that you can use for simulations of gas dynamics. But before that, let's discuss the some theory. So we discussed when we discussed scalar conservation laws, we introduced the concept of weak solution. So what is the weak solution? A weak solution of the nonlinear system or first-order system of hyperbolic equations is any piecewise differentiable function that satisfies to the following condition for any choice of contour in plane xt. So the weak solution of this equation is the solution of integral form of this equation. So weak solutions are the solutions that can be obtained from integral form of equations. And we obtained our numerical method from the approximation of integral form of equations, although it looks like the same as finite difference maybe method. The problem, so this is the slide from our previous lecture. And so this is a very meaningful slide. So once again, we discussed just that for linear problems we have flux equivalence theorem. For the linear case, for linear problem, for linear schemes, we have the convergence, consistency, and stability. And in the linear case, the convergence is equivalent to stability for the consistent numerical scheme. But in the presence of discontinuities, it can be shown that most numerical approximations are not consistent for non-smooth solutions. So, for example, Lax-Wendroff method does not converge in the presence of discontinuities. So it means there are two outcomes. So the first one, the Lax equivalent theorem cannot be applied in the simulations we are discussing now with finite volume method, with discontinuities, with the integral equations, and so on. And the second, so we should have something else. So Lax equivalent theorem doesn't work. And actually, it also means that we should introduce some other definition of stability. And actually, we will do it later. And now, instead of flux equivalence theorem, here there is another theoretical statement. It differs from Lax equivalent theorem. It's not the same, but also a very powerful statement. So let us consider a conservative numerical method. So our numerical method should be conservative. For example, finite volume method. We are assuming that numerical flux is consistent with the differential flux. So the definition of consistency here for problems for equations that admit discontinuous solutions also is not the same. We are not able to use this Taylor series expansion. But I'm not going to discuss it in detail. But so we're assuming that numerical flux is reasonable, is consistent with the differential flux. If the numerical solution converges under the following condition, so h goes to 0, tau goes to 0, then it converges to the solution of the problem, to the weak solution of the problem. So the Lax-Wendroff theorem states that if we compute our numerical solution using a finite volume scheme on a set of grids, and we can see that we have convergence, then we can be sure that we obtained some weak solution of our problem. So it doesn't guarantee us that the scheme will converge under some conditions. It just states that if we see the convergence and the numerical scheme is good enough, it's a finite volume method, and the numerical flux is reasonable, and we can see the convergence, then we have the convergence to weak solution. And that's very strong statement. You can find the details here. And this is also a very informative picture. So what is the difference from practical point of view between simulations using conservative and non-conservative schemes? So for sure people try to use conservative schemes, but actually it's possible to solve, so it's possible to generalize this scheme to a nonlinear problem. And you can see that here, if you build your numerical scheme as some approximation of this derivative and this derivative, you can after that check if the scheme is conservative. You can choose some control volume and compute the integral, compute the changing of your quantities inside this volume. And nothing here guarantees the fulfillment of conservation property. Here we can be sure, because we built our numerical scheme as an approximation of balances. And here is just approximation of subderivatives, and that's the problem. So if you will use the non-conservative scheme, one of typical behavior of this scheme is that the speed of propagation of your disturbances is wrong. So if your scheme is conservative, even if it's not monotone like here, so suppose this is the exact solution and the dots correspond to the numerical solution, and you have this overshooting, undershooting, that's it. But the speed of propagation of your disturbance in simulations is correct. But if you have non-conservative scheme, the typical behavior is that your waves, they propagate with the wrong speed. You have a phase error, and that's also very bad. behavior, because once again, so the oscillations are better than their own speed of disturbances propagations of propagation in your model. So this is one of the most mathematically rigorous statement in this field. Although there are other statements based on nonlinear definition of stability. Maybe we'll discuss it later. But this is maybe this one of the most important. This was published in 1960, again, in the work of Lux and Wendroff. Okay. For many times I've mentioned that we are solving hyperbolic problems. So, but what does it mean? We need to provide mathematically rigorous statement for that. Definitions of hyperbolicity. So suppose we have this system of quasi-linear equation of the first order written in the quasi-linear form. So here U is a vector of Ri, and A is a matrix from Ri by I, and A is it's a matrix, but it's a nonlinear matrix. So it depends on a known function U. And we actually can have some right-hand side, but actually we will skip it. We'll cancel it. This system of equations is called hyperbolic if the following conditions are valid. So the determinant of I minus lambda E, where E is identity matrix. So if we solve these equations, we will get the eigenvalues, right? And so the first requirement is that eigenvalues of this matrix should be all real. So this is the first requirement. And the second requirement, we would like to compute the right eigenvectors. So this is just you can check the books on linear algebra if you have some problems. But you can compute the right eigenvectors corresponding to these eigenvalues. You will get them. And the second requirement is that these right eigenvalues, they form a basis. It means that if we create a matrix with these columns omega r, its determinant will not be zero. So this system of partial differential equations is called hyperbolic if all eigenvalues are real, and the matrix and the right eigenvectors, they form a basis. Two requirements. If it is so, there are some distinctive features of such system of equations. For example, the presence of finite propagation velocity of infinitely weak perturbations. We will discuss it. So it's a sound. So if you have the system with such properties, it means that in this system you will have the disturbances like sound waves and gas, possibility of existence of discontinuous solutions even for smooth initial data, the mechanism of formation of shock waves, gradient catastrophe. So all these things that we discussed for scalar conservation law, so this expansion waves, compression waves, formation of shocks, and so on and so forth. So in the case of system of nonlinear system, system can have or have has the such properties if it's hyperbolic, and it's hyperbolic if all eigenvalues are real. And so this determinant is not zero. There are a lot of different hyperbolic models. So we're interested in gas dynamics, but actually there exist other hyperbolic models. Dealing with nonlinear system is a bit difficult. Let's start with linear system. So let us consider first a linear homogeneous system. I mean system with right-hand side term equals 0. So let's start. So what are we going to do? I want to construct the finite volume numerical scheme as a generalization of Courant-Jackson Rees numerical scheme. So we discussed the property of this scheme. It was our first numerical scheme that we started for linear advection equation. Now I want to show how can we use this scheme for order equation. Okay. For that, we should work with the matrix of our equations. Let's start with, first of all, with the linear system. So suppose that matrix A does not depend on U. So A is constant. There's some values. And at the same time, the system is hyperbolic. I mean that all this is true. If it is true, it is known that A can be presented as a product of omega r, lambda, omega l, where omega r is a matrix of right eigenvectors of our matrix A, lambda is diagonal matrix of eigenvalues, and omega l is omega r inverse. So actually it's a matrix of left eigenvectors of matrix A. So it's possible. So it is known that for the matrix of hyperbolic. So it's just again from linear algebra. So for analytical geometry, for matrix of hyperbolic system of equations, the following representation is valid. Okay, we can put it to our system of equations: d over dt plus a that can be represented as such product du over dx. What is the linear system of equations hyperbolic? So one of the most known equations in our field, the field of gas dynamics, is acoustic system of equations. So Euler equations can describe the motion of any compressible media with strong disturbances. For example, with strong shock waves after explosions or something like that, where you have big changes in density, pressure, velocity, and so on. But if we say that so density of the media is constant and the pressure is some initial pressure plus very small correction. So I mean, if you say that all the parameters in our system, they are very small disturbances, so we can linearize our system of equations, Euler equations, and get the so-called acoustic system. So it describes the propagation of sound waves, for example, and this system is linear. So here we have, we suppose that density is constant, speed of sound is constant, and we have only two variables, p and u. I mean, density and velocity. And so the linearized system of Euler equations is acoustic system, and it is an example of a linear system of hyperbolic equations. Okay, so I explained to you some, just common general approach how to deal with hyperbolic systems. We have this representation of A, put it here, and then we multiply from left and right of this equation by omega r, not omega l here, but omega l times omega r equals to identity matrix because of this connection we have here. And then we consider only a linear case. So A is constant. It means that we can put omega l here into the brackets, parentheses, and get this this equation. So we can introduce new variables called Riemann invariants, omega l times u. And if we introduce these new variables, we can rewrite our initial system to this form: dr over dt plus lambda dr over dx equals 0. What was lambda? So lambda is a matrix with zeros and only with eigenvalues on the diagonal. And it means that this system of equations decouples into a number of independent equations. So Riemann invariants are the variables in which we can rewrite our initial system of equations as a set of independent equations. So the problem was that initially, you can see here, for example, our system of equations is coupled. So we have du over dt here and dp over dx here. It means that if we will try to build some numerical scheme, is very in a simple way. For example, let's substitute this as using explicit order scheme, and this substitute using some left or right angle scheme. It will not work. So because the functions are different, so it's not just the same function. So if you take initially, we have the coupled system of equations. And if we compute Riemann invariants, in these variables, we have independent equations. So we have I equations where I is the number of unknowns. But here, Ri is not pressure or velocity or anything. It's some combination of these variables. And for some combination, our system of equations decouples into a set of independent equations and corresponding to each eigenvalue lambda. And I can remind you that all these lambda are real. And so because we consider only hyperbolic equations. As you can see, actually, formally, so once again, it's not only for gas dynamics. So if you know this, so that is why the numerical methods that were developed for gas dynamics actually can be applied not only for gas dynamics. So if your method for hyperbolic equations is based on these matrices, omega, lambda, and so on, and you know them for gas dynamics, if you know them for another model, okay, you can also apply the methods that we developed originally for gas dynamics to another models. So okay, for linear system of hyperbolic equations, we introduced the Riemann invariants. And so I explained what does it mean. And now we can apply the known methods for linear advection equation to these equations in Riemann invariants. Not to initial equations, but these, because we have here this function Ri is the same. So okay, let's apply our Courant-Jackson numerical scheme to these equations obtained after this transformation from our initial problem. So this is just Courant-Jackson Rees numerical scheme that I have already written today. We just use the notation G for numerical flux. So once again, it's just the same as this, not this. So I use this form of notation, but instead of U, we have Ri, instead of F, we have G. Yeah. This is component-wise notation. I is from 1 to I. Then we should move to vector notation. So collect all these equations for each I into one vector. And now we have the scheme, numerical scheme for Riemann invariants, right? So they are these variables. So U is our initial variable, such as velocity, density, pressure, and so on. R some combinations between them. And first of all, we are able to build good numerical scheme. I mean, we can expect that the properties of our numerical scheme, Courant-Jackson Rees numerical scheme, so they will be the same here. So we have numerical scheme for Riemann invariants, right? And here not lambda, but this matrix lambda. And then we should move back to our initial variables, U, because we usually would like to think in terms of velocities, pressures, and and so on. That is why we should also move back to U. That is why we write that Riemann invariant R is omega L U. Okay. So we substitute all the Riemann invariants using this definition, and after that we multiply from left and right by omega L inverse. And then we get this numerical scheme written in our for our initial variables U. That's okay. But now we obtain the numerical flux that follows from Courant-Jackson Rees numerical scheme. So this is the generalization of our Courant-Jackson Rees numerical scheme to the system of hyperbolic linear equations. So here we can have this combination equals our matrix A, but here is not matrix A. Here is model lambda, right? Because of this model lambda. You can carefully check that if you do these manipulations, they are simple. You will get this numerical flux. And so, but now we have the numerical flux for linear system. Vector form. It is already vector form. Yeah. Yeah, actually we started with quasi-linear form. and we formulated the definition of our system for quasi-linear form. But now let's rewrite it for conservation form. So this is our initial system of equations. So we consider A is constant, then we can rewrite it as du dt plus df over dx, where f is AU. And then here, it's A, AU is f, right? That is why here we have f and f, f and f. So we just rearrange to write our equations. That once again, we still solve the linear system of equations. But here we're not able to write A once again, because here we have model lambda. And model lambda comes from, you can remember we provided two forms for Courant-Rees numerical scheme depending on the sign of lambda. So, and we keep this generalization, and now we have the whole system of equations. But the most interesting thing now is how can we use it for nonlinear system of equations, for the Euler equations. For the Euler equations, we can provide just this generalization. So suppose now we have Euler equations or some other nonlinear hyperbolic equations, d over dt plus f of u dx equals 0. But now we just say that we can generalize the same formula. So that's not mathematically rigorous. One more time. So this is mathematically rigorous. We obtained the generalization of Courant-Rees numerical flux to the linear system of hyperbolic equations. And the next step we say, okay, just use the same formula. Our finite volume method. This guy is understandable. The most problem is here. The most problem is here. Because for linear equations, all these matrices are constant. Omega r, lambda, omega l. And we need to compute numerical flux through the boundaries through the edge between m plus 1 and m. Which values should we take here to compute the matrices? So the problem is here, how to compute the parameters at the boundary between two cells. And within this general framework, different authors provided different answers, and actually they obtained different numerical schemes. For example, I have already mentioned Professor Kholodov from department where I worked, and he proposed just simple averaging between this combination of matrices to the left and to the right. The well-known paper of Phil Rowe, he proposed some averaging for values between um and m plus 1. I'm not going to explain you in detail, but he provides some idea how to compute the. Actually, I have shown to you when I shown you how the reflection waves, how can reflection shock waves obtain in simulations, or we can use some other formulas how to approximate these values, and obtain so-called Rusanov numerical scheme, or actually Friedrichs numerical scheme. So on such a way, you can obtain also the generalization not only Courant-Rees scheme, but also Friedrichs numerical scheme. And that's it. Actually, this is I provided you 1, 2, 3, 4, 5. In fact, different formulas for numerical flux calculation, but they all exist in grid. So it's called grid characteristics ideology of how to compute the numerical flux for the Euler equations. So we started with the Courant-Rees numerical scheme for linear direction equation, obtained it for the system of linear equations, and then generalized it for the system of nonlinear equations. And to use it, actually, I have a program that was developed for educational purposes, and one of the next lecture will be about, I will explain how it looks like and the main parts of this program in which I implement this numerical flux. So if you want to use this numerical flux in reality, in practice, what do you need? You need these matrices. So for all equations, what is F? Let's check that we understand what's going on. For all equations, F, the capital, is this one, computed at mn, right? So so this capital F m plus 1 is just our flux computed from this our grid function m plus 1 n. Okay, and the only problem, we need these matrices omega r, lambda, omega l. So how many times do we have? Still have some time. I think maybe it's a bit difficult for you, but I will show. To use this matrix, you should analyze the properties of matrix of the Euler equations. Actually, it has already been done in many books, and you can just use it. But I'd like to explain to you how to do that. So, what is a matrix for the Euler equations? So let's start with this conservation form: d over dt plus df over dx equals 0. So this is vector of conservative variables. This is a flux vector. And what is A? So A is Jacobian matrix. We should compute df over du. And is 3 by 3 matrix. dfi over dug, ig from 1 to 3. For example, consider element A11. So it's a bit difficult because we have independent variables rho v, or so v is velocity here, and e, not rho p and v, but some combinations. And so we need to compute the derivative d, for example, d rho v over d rho. It equals 0 because rho and rho v are independent variables. Okay, that is why a11 equals 0. Then we compute a12. a12 is the partial derivative of df1 rho v over d rho v. That is why unity. And then a13 equals 0 because df1 rho v and e, they are independent variables. That is why the first row of matrix A for the Euler equations is very simple: 0, 1, 0. But this is the second one, a21. We need to compute the partial derivative of df2 over du1. What is df2? This is the second component of our flux vector, right? Rho squared plus p, and we compute the partial derivative of u1 over rho. How can we do that? Just the derivative of complex function. Okay, just rewrite it, and then we changed rho v squared as rho v squared over rho. So we multiply and divide the same this by rho, and the pressure is a function of density and internal energy, because here we have such set of independent variables. We can accurately compute it and obtain the expression for the component of Jacobian matrix. Moreover, it is written for the general equation of state. So we keep here the derivatives dp over the rho for the fixed internal energy, and dp over the epsilon for rho. And in the same manner, we can compute all the components of our Jacobian matrix and obtain this matrix A. After that, it's possible to compute the eigenvalues of this matrix A, and the eigenvalues will be v plus c, v minus c. This is a very famous result. Actually, you can obtain these eigenvalues in simpler way, because if you will use the non-conservative variables to write your system of equations, so all this will be much simpler. But if you want to use finite volume scheme based on this matrix A, you should have this matrix A. What is important here? So the eigenvalues of matrix A for the equations are v plus c, v minus c, where c squared is the following combination. So it's just formal analysis. So it's possible to do analytically. That's not very difficult. I can also submit you a document with this, mathematics. It's very easy. However, what is c squared? You can check that this c squared is just the speed of sound. So from formal analysis of the Euler equations, we obtained that eigenvalues of Euler equations are v plus something, v minus something. And this something is exactly square root of c squared. So it equals gamma p over rho for the ideal gas equation of state. It means that so this speed of sound can be obtained from different considerations, from some intuitive physical assumptions, but it also comes from rigorous mathematical analysis of the Euler equations. And you can see here a lot of very important outcomes. So you can see V minus C. So V is speed of gas, or velocity of gas, and C is speed of sound. It means that if you have subsonic, supersonic, transonic flow, your eigenvalue will change your sign, and that is why you will get difficulties, or you can get difficulties in numerical solution of your equations, because for different speed of for different velocities, the behavior of your characteristic line changes. That is why people 50 years ago, or I don't know, 60 years ago, so they developed different numerical methods for subsonic flow, for supersonic flow, for transonic flow, because the properties, so the structure of the properties of the flow change drastically. Anyway, what is matrix lambda? Is a diagonal matrix with eigenvalues on the diagonal, and also it's possible to compute the matrix consists of right eigenvectors and left eigenvectors. So for all your equations, all these matrices are known. They are described. You can find them in book. Moreover, not only for ideal gas, but for equation of state of compressible media written in some general form. So you can even use, I don't know, not analytical expressions, but these derivatives can be obtained from some, I don't know, tables and so on. So this approach that I described not only comes from, good Courant-Jackson Rees numerical flux, it contains a lot of numerical schemes depending on the closure or how can we compute this m plus 1/2 value, and also can also be applied to even non-ideal gas. Well, okay, I understand that maybe it's a bit difficult to you, but actually I hope that the main ideas are clear. And all this mathematics is not too important. Actually, I can provide all the necessary material, and you can find it in books as well, which I provided to you. But the most important is the idea. For sure, is without these explanations, it can be a bit confusing, because here, for example, independent variables are not rho, v, and p, but some complex. That is why you should be careful here. Be careful here. Okay.